And the x dt is just how fast this object's going in the x direction, which is vx right there, the way I have it labeled. So this becomes vy over gamma 1 minus u vx over c squared. All right, so these are important enough, I'm going to write them up here. So we had W equals V minus U over U V over C squared. V Y prime equals Vy over gamma 1 minus U x over C squared. Questions to hear? I will tell you this, the perpendicular movement, or the velocity perpendicular to the movement of the prime frame, this is going to save us about an hour's worth of board work. A couple years ago, I was doing the E equals mc squared, and there was a derivation I had done it, which was relatively simple. And there was something that had been bugging me, but I still went through with it, no one ever questioned it. And there was one particular class where I was in the middle of it, and suddenly I realized what had been nagging at me for a couple of years. And that it just basically was wrong. It was a bad derivation. Later on, I went and looked, and I thought, I got it from somewhere, and I looked and I found the source where I got it from, and they said this is the derivation of it, but there was a mistake. It wasn't the right derivation. So I attempted to do a last minute, trying to do a proper derivation of E equals mc squared. And it was just one of those days, it just wasn't clicking. After about an hour, I said, I'm done, just go. Just because my brain was just not, it wasn't happening. Then I figured out that I prepared better for the next week. Went through the grueling hour-and-a-half derivation. But then, last summer, I found a quicker one. So, if you want the grueling hour-and-a-half derivation, I'll be glad to do it for you. Sounds like a groundswell against it. I know, I built it up, didn't I? Now, the one thing the two derivations have in common, the two legitimate derivations have in common, are conservation of momentum. So, again, we're going to go with our, well, S frame and S frame and S prime frame. And in the S frame, I'm going to have an object that is traveling in some particular direction, traveling in the Y direction. And then at this point right here, there's going to be a force applied to it. Matter of fact, that force is going to be applied to it for this region right here. And so it starts out going some speed, u sub naught, and u sub naught is slow. It's close to zero. It's not zero, but it's close to zero. So this object just puts it along in this frame, and then suddenly a force is applied to it. Some force is applied, and it zips. And the components here are V and U. I don't think I need the hypotenuse there. No. So let's just look at it from the S point of view. What is the relationship between force and momentum? And time, if you want to throw that into it. see whoever was your 251 instructor who made an incredible impact upon you. How about the obscure clue when suddenly someone buys you flowers?
Is it impulse?
There we go. Thank you. Impulse. What is impulse?
Changing momentum.
Or
T finalized T initial.
true, that is true. Force times time. Yeah, change. Force times time. It'd be average force times time. We're gonna make the force constant just to make life simpler there. Another way of going about this is that Newton's second law, F equals ma, which is m times dv dt. Newton assumed that the mass was constant, and so this would be dmv dt, which is dp dt. But that's the more generalized. The force is dp dt is the more generalized Newton's second law. So we have a force here that's being applied. The force that is applied is just f of x in the I hat direction. And so let's go ahead and find I hat, j hat. So force, which is f of x I hat, equals d px I hat plus py j hat dt. So force is just equal to momentum times divide momentum, the time derivative of momentum. Now, since the force is only in the I hat direction, the j hat part must be equal to 0. So dpy dt must be 0. Then f of x must be equal to dpx dt. It's this part right here that matters to us. Now, in Newtonian physics, the mass doesn't change, and so U and U sub naught should be equal to each other, but we're dealing with relativity, so mass is not constant, and so as the mass increases, U will change also. Py is constant. Therefore, Py initial is equal to Py final. And my Py initial is M sub naught U sub naught. This was my reason for making U sub naught really slow here, is so that the mass is close enough to the rest mass. I cannot make that assumption in the second case. So final, this would be M times U. Obviously, we're not there yet. We're not done yet. But we do have this relationship that M naught U naught is equal to M U. Now, let's look at the path of this particle from the S prime's point of view. I want to make S prime travel at some speed v. So S prime is going to be traveling basically with the same speed that this particle is going to be traveling after the force is applied in the S frame. So in the S prime frame, this is my Y prime and X prime. The particle in the S frame is going up like this. In the S prime frame, which way will it be going? S prime is shooting this way, while this particle is moving up like that in the S frame. If you need sort of a visualization, we'll assume this room is the S frame. I will be S prime. All right, so, Marisol, if you would just lift your hand slowly. From my point of view, what does it look like her hand is doing?
Going up.
Pardon?
Going up.
And that way. Yeah, it's moving away from me.
Up.
From my point of view, all of you are moving that way. So it's moving this way, and then a force is applied. And then it's going straight up. So this is initially going in that direction. Now, the speed at which your hand is going up will be u naught prime, and this will be some speed v. Mass m, and mass m sub naught. The exact same logic as before, py prime is constant. In other words, py prime initial equals py prime final, or m u naught prime is equal to m sub naught u prime. So that'd be prime there. So I have these two relationships here. So let's do some dividing. I want to divide left sides and right sides. So I have m naught u naught over m u naught prime is equal to m naught, oops, sorry, equals m u over m naught u prime. So basically divided the left sides and then divided the right sides. And hopefully copy this down correctly. I'm going to multiply both sides by m naught over m and by u naught prime over u naught. In other words, I'm getting all my m's over on the left-hand side, the u's on the right-hand side. So I have m naught squared over m squared equals u naught prime over u naught times u over u prime. Recognize that these u's are the velocities that are perpendicular to the motion of the prime frame. And conveniently, we just came up with a formula to relate those two. All right, so u naught prime over u, I need that relationship. Over u naught, and then I need the relationship of u over u prime. All right, so beforehand, we have u naught and u naught prime. The difference is that the object is speeding towards you. That's the, I guess, prime frame is going away. The particle is moving towards. So we have u naught prime is equal to u naught divided by gamma 1 minus, and that would be the speed of the prime frame with respect to the frame times times 0. See, so it's the speed of that, and then v sub x. Yeah. This v sub x was how fast the particle is moving relative to the non-prime frame, which was 0 over c squared. So this is u naught over gamma. Therefore, u naught prime over u naught is 1 over gamma. Okay. We'll do something similar over here. I know that u prime, let's see, I want to do it u prime is equal to u over 1 over gamma times 1 minus the speed of the prime frame with respect to the object, and then times the speed of the object with respect to prime, so v squared over c squared. Gamma is 1 over the square root of 1 minus beta squared, and I'm multiplying that times, this is my denominator here, 1 minus beta squared. So this becomes the square root of 1 minus beta squared. Actually, and that's just the square root of 1 minus beta squared. So this becomes u over the square root of 1 minus beta squared, which is just gamma times u. So u over u prime is equal to 1 over gamma. So m naught squared over m squared equals 1 over gamma times 1 over gamma, which is 1 over gamma squared. Put in more traditional form, m squared is equal to gamma squared m naught squared. So m equals plus or minus gamma m sub naught. Obviously, the negative solution is not really working for us here, and we're left with gamma m sub naught equal to m. This is the relationship that talks about the faster an object goes, the more its mass increases. And that's important enough to write off to the side because we will use that in our last step. So the mass of an object is equal to gamma times its rest mass. Now, for some unknown reason, the rest quantity is often called the proper. We had proper time, we had proper length. Technically, it's a proper mass, but I usually just see m sub 0 for rest mass as opposed to m sub p for proper mass. Questions to here? The last step is relatively simple. Well, at least compared to that horrible hour-and-a-half version of this that we just did. All right, tension's mounting, everyone's excited. We can do this. We got the prime frame, the regular frame, that hasn't changed. We'll erase that when we need it. M equals m sub naught, gamma m sub naught. M is equal to 1 minus, oops, try that again, 1 over the square root of 1 minus v squared over c squared. I guess u in the last context we were doing, I'm pulling back to v here, just because. Multiply both sides by the square root, I get m sub naught. My rest mass is equal to the square root of 1 minus v squared over c squared times m. We don't like radicals, so let's square it. M naught squared equals 1 minus v squared over c squared times m squared. Let's multiply through by c squared to distribute. Let's do it all. So m naught squared c squared equals m squared c squared minus v squared n squared. Yeah, it's true. Unless I made a fatal error. Nope. Seems to match what I have. At this point, let's do a derivative. So what are my variables? If I'm gonna look at some differentials here, what can change?
I guess mass and velocity could change.
Yep. What about m sub 0 or c? All right. So when we take so if we do a derivative here, or at least do our differentials here, this is 0. This isn't going to change. So 0 equals, well, c is constant, so this becomes 2mc squared minus 2vm squared minus 2mv squared. I have 2m common to everything, so I can get rid of some stuff there, using the technical term. So I'll get rid of 2, m, one of those, and that m. So we've now been reduced to 0 equals c squared minus vm minus v squared. Oh, man. What did I forget? In this line right here,